A singly linked list is a data structure that consists of a sequence of elements, where each element points to the next one in the sequence. Each element in a singly linked list is called a node, and it contains two parts, data and a reference, or link to the next node in the sequence. The last node typically has a reference pointing to null, indicating the end of the list. Now we will see a simple implementation of singly linked list in C. This C program demonstrates the implementation of singly linked list with basic operations such as creating a node, inserting a node at the beginning and end, printing the linked list, and freeing the allocated memory. Now let us see the code. Include headers. Hash include stdio.h. This line is a preprocessor directive indicating that the program is going to use the functions and declarations from the standard input-output library, that is stdio.h. This library provides the functions for reading and writing data, such as printf and scanf. Hash include stdlib.h. This is another preprocessor directive specifying the inclusion of standard library for general purpose functions, that is stdlib.h. This library includes functions for memory allocation such as malloc, free, etc. and other utility functions. These two lines are common at the beginning of the many C programs, as they include essential libraries that provide fundamental functionality for input, output, and general purpose operations. This is the node structure, where int data is a member of the structure representing the actual data stored in the node. In a linked list, each node typically holds a piece of data. This is a pointer to the next node in the linked list. It creates a connection between nodes forming a sequence. The struct node pointer indicates that this pointer is expected to point to the another node of same type, that is node. If the node is the last in the list, the next pointer is often set to null to signify the end of the list. This structure allows you to create the linked list where each node contains an integer value, that is data and reference to the next node. The linked list can be traversed by starting from head node and following the next pointers until reaching the end, where next is null. Now we will create a node that dynamically allocates a memory for new node in a linked list and initializes it with given data. Here, int data is a parameter that represents the data that you want to store in a newly created node. This is the function declaration. It specifies that the function returns a pointer to a struct node, indicating that the function will create and return a new node. This line dynamically allocates memory for a new node using the malloc function. The size of struct node ensures that enough memory is allocated to hold a node structure. The cast struct node is used to convert pointer written by malloc to the appropriate type. This block checks if the memory allocation was successful. If malloc returns null, it means that there is not enough memory available. In such case, an error message is printed and the program is terminated using exit 1. Once the memory is successfully allocated, the function initializes the new node's data with provided value and sets its next pointer to null. This prepares the node for the insertion into a linked list. Finally, the function returns the pointer to the newly created and initialized node. The calling code can use this pointer to incorporate the node into a linked list. This function is useful for dynamically creating a new nodes that can be easily inserted into a linked list. Now let's define a function named insert at the beginning that inserts a new node with the given data at the beginning of the linked list. This parameter is a double pointer pointing to the head of the linked list. Essentially, it's pointer to the pointer that holds the reference to the first node. The use of the double pointer enables the function to make changes to the original head pointer in the calling code. Int data. This parameter represents the data that you want to store in the new node. This line creates a new node using the create node function. The create node function dynamically allocates memory for a new node, initializes it with the provided data, and returns a pointer to the new node. This line updates the next pointer of the new node to point to the current head of the linked list. This step ensures that the new node becomes the first node in the list. and its next pointer is set to the existing head. This line updates the head pointer to point to the newly created node. After this operation, the new node becomes the first node in the linked list, and it is linked to the rest of the list through its next pointer. In summary, the insert at beginning function inserts a new node with the given data at the beginning of the linked list. It does so by creating a new node, updating its next pointer to point to the current head, and then updating head pointer to point to the new node. Now let us define a function named insert at end that inserts a new node with the given data at the end of the linked list. This parameter is a pointer to the head of the linked list. It's a pointer to the first node's pointer. Using a pointer to a pointer allows the function to modify the original head pointer in the calling code. Int data. This parameter represents the data that you want to store in new node. This line creates a new node using create node function. The create node function dynamically allocates memory for a new node, initializes it with the provided data, and returns a pointer to the new node. This block checks if the linked list is empty. If it is, the function sets the head pointer to the new node, making it the first and only node in the list, and then returns from the function. This block traverses the linked list to find the last node. It starts from the head and iterates through the list until it reaches the last node, where temp is greater than next is null. After finding the last node, this line updates the next pointer of the last node to point to the newly created node. This operation effectively adds the new node to the end of the linked list. In summary, the insert at end function inserts a new node with the given data at the end of the linked list. It creates a new node that handles the case where the list is initially empty, and then traverses the list to find the last node before updating its next pointer. Now let us print the list function. A function named printList that traverses a linked list and prints the data of each node. This parameter is a pointer to the head of the linked list. It points to the first node in the list. This line initializes a temporary pointer temp to the head of the linked list. This temporary pointer is used to traverse the list without modifying the original head pointer. This block is a loop that iterates through the linked list. It continues until the end of the list is reached, that is, temp becomes null. Within the loop, the function prints the data of the current node using the printf %d temp is greater than data, and then moves to the next node by updating the temp pointer to point to the next node, that is, temp is equal to temp is greater than next. After the loop, this line prints a new line character to move to the next line, providing a clean separation after printing all the node data. In summary, the printlist function takes the head of the linked list as a parameter and prints the data of each node in the list. It uses a temporary pointer, that is temp, to traverse the list and while loop to iterate through the nodes, printing their data. Now we will free the list function. Function named freeList that traverses a linked list and frees the memory allocated for each node. This parameter is a pointer to the head of the linked list. It allows the function to modify the original head pointer in the calling code. This line declares a temporary pointer temp that will be used to traverse the linked list. This block is a loop that iterates through the linked list. It continues until the end of the list is reached, that is, the head pointer becomes null within the loop. This line assigns the current head node to the temporary pointer temp. This step is necessary to ensure that we don't lose the reference to the node that needs to be freed. This line updates the head pointer to point to the next node in the list. It effectively removes the current node from the list. This line frees the memory allocated for the node pointed to by temp. It deallocates memory used by the node, preventing the memory leak. After the loop completes, the function has traversed the entire linked list, freeing the memory of each node. The head pointer is set to null to indicate that the list is now empty. In summary, the freeList function takes a pointer to the head of the linked list, traverses the list, and frees the memory of each node, ensuring proper memory cleanup. Now let us see the main function of this program. This line declares and initializes a pointer head to type struct node. It's initially set to null, indicating an empty linked list. These lines insert elements at the beginning of the linked list. The values 1, 2, 3 are inserted. These lines insert elements at the end of the linked list. The values 4 and 5 are inserted. This line prints the linked list using the printlist function. This line frees the memory allocated for the linked list using the freelist function. After this, the linked list is empty and the memory has been deallocated. This line indicates that the program has executed successfully and returns 0 to the operating system. The output will be linked list 1, 2, 3, 4, 5. In summary, the main function demonstrates the creation, modification, printing, and cleanup of a linked list using the provided functions for insertion at the beginning and end, printing and freeing the memory.
Like, comment, and subscribe.